how information travels across the world. It also aims to increase awareness of how crucial communication is in our lives and stimulate the development of technologies in the field. This day marks the anniversary of the signing of the first International Telegraph Convention and the creation of the International Telecommunication Union. The theme for this year is Accelerating Digital Transformation in Challenging Times. The COVID-19 crisis has not only highlighted the critical role of information and communication technology for the continued functioning of our society. Digital transformation is about improving each citizen's experience and improving quality of life, while ultimately aiming to meet United Nations Sustainable Development Goals. Today, to celebrate this special day, we have organized a special talk on some glimpses of 5G research at IIT Delhi. The talk will focus on understanding the key differentiating features of 5G, followed by brief highlighting some research work on 5G at IIT Delhi. I'm extremely delighted to let you all know that today we have with us Dr. Nilima Jairath, Director General Science City, Dr. Savdesh De, Professor, Department of Electrical Engineering, IIT Delhi, and Dr. Rajesh Grover, Director Science City. I very heartily welcome you all. Before I request Dr. Nilima Jairath to give inaugural remarks, I would like to share her brief profile.
Please keep it brief. Please keep it
brief. Sure. Dr. Jairath is PhD in botany with specialization in ecology and environmental science. Prior to joining PGSC, she was Executive Director of Punjab State Council for Science and Technology. In recognition of her services, she was awarded Punjab State Government Award from the Chief Minister of Punjab in 1999. So, ma'am, may I request you to kindly give the inaugural remarks?
Thank you so much, Ritesh. A very good afternoon, Professor Day, and all the participants who are with us today. All the students, all the children, all the teachers who are with us, and in case there are any members from the general public, a very good afternoon to all of you as well. When I was told that we are going to celebrate the World Telecom Day, I remembered, because I belong to a generation where as a child I have been introduced to the telephone system or telecom through the dial telephone. Now, the other day I was talking to a group of youngsters who couldn't understand how a dial telephone works. And today we are talking about 2G and 3G and 4G, and now it is 5G, which we are talking about today. So at this occasion, we intend to celebrate the power of telecommunication, how it has become such an important part of our lives. I remember that when I was a child, there were very few houses where a telephone would be there, and it used to be a big luxury. And there was this concept of a PP phone, which meant that you had to, if you didn't have a telephone connection yourself, you could give somebody else's number and the charges were slightly higher. There would be an operator who would actually call you before you are linked to the other person to whom you want to call. It was such a difficult and a long process, but an enjoyable all the same. But today, every one of us has a phone in our hands. And I think our lives have, we are totally dependent upon our phone. There was a time when I used to remember a lot of telephone numbers. Now I hardly remember any telephone number because I don't need to remember it. So there are pluses and there are some minuses, but at the same time, yes, it is very, very important. This technology has impacted our lives so very greatly, especially in this COVID times. The telecommunication sector has become so handy in communicating with each other, in conducting classes, and even, I would say, even in Pushpa Gujarat Science City, about till 2 years ago, if somebody would say that we want to do a program, the first question was, How do we get it funded? And how do we get children interested to come and visit science? Now, today, with the power of telecommunication, we are all sitting together on a platform. We are connected to each other. We can talk to each other. We can look at each other, and we can interact and learn from each other. So you don't actually have to physically travel if you really are interested in getting information about something. The information is in your hand, I would say, because it is in the phone which you hold. And if you look at little children, I have grandchildren, and perhaps they are much more comfortable than me while using a phone. So today we have got a luminary in the field, Dr. Day from IIT Delhi, and it is indeed a great pleasure, sir, that you agreed to speak to our students at this occasion. A very warm welcome to you from my personal side, as well as from the side of the entire staff of Pushpa Gujarat Science City, and as well as from the side of all the participants who are here. We look forward to your talk, and we look forward to learning a lot from you. Um, Hundreds and millions of people are dependent upon these networks to access real-time information. And the telecom sector has actually helped us realize this. So without yeah, getting in between you and the audience, I would like to hand over the platform to you. But before that, I would request Mr. Pathak to kindly introduce the speaker of the day. Mr. Pathak, please.
Thank you, ma'am. Now, before I invite Professor Day to begin today's session, I am privileged to share his brief profile. Professor Day is professor with the Department of Electrical Engineering and also an institute chair professor at IIT Delhi. He has widely contributed through cross-layer optimization research in communication networks. His research interests are broadly in communication network with emphasis on performance, modeling, and analysis. To date, he has published over 90 articles in top journals, over 100 papers in well-known conferences, 1 US patent and filed 5 Indian patents. His publications have been widely cited with nearly 4,000 Google Scholar citations. Professor Day currently serves as an area editor for Institution of Electrical and Electronic Engineers, Communication Letters. So this was the brief profile of Professor Sabdesh Day. Now I request Professor Day to begin today's session.
Thank you, Dr. Jirat, for your kind introduction, and Mr. Pathak for introducing me for the talk. And also thank you for the invite. This is I'm not a good speaker. This is a challenging process for me to speak in front of a large audience and who are all invisible. So I would like to, as I move, because of this volume of audience, possibly we cannot interrupt in between. So I would request all of you to keep your questions or queries noted down, and at the end of the presentation, we can take up as much as possible, as many as possible, to briefly explain. And let me share the slides, and hopefully this is visible, and I'll also make it full screen. Screen mode, okay. Okay, so in fact, the title originally, my thought was to give an overview of the many different problems. Then I thought, okay, let me try to go into one particular direction, and within that direction, still we are doing a lot of work. And so my preparation for this talk today is for the researchers and the students who would like to take up research as a future prospect, research or maybe research and development in industry also. Very much welcome. And so I might assume several the basics known to you. However, if you feel that these are not in place, please make note and feel free to ask me at the end. And if you feel that if you are pressed to ask the question, in fact, I would request Mr. Pathak to somehow intervene, and if needed, I can stop in between, because I normally like to take questions in between so that I know where I stand in front of the audience understanding. So let us see how it progresses. And also, in fact, to give an overview. So first of all, this is my talk outline. I have a very brief, in fact, one slide overview of 5G. What is meant, basically the key aspects of 5G. And then I have collated a few topics around one of the very pertinent areas that I have been working on, energy harvesting. And then I will also connect why this topic is very relevant to this 5G. And then further towards the end, I'll also highlight some of the other research that are going on. These are also connected to 5G research, and then we'll summarize the discussion today. Okay, so one slider, however, I'll try to explain. So basically, as ma'am has mentioned, that we have moved from 2G, 3G, 4G. In fact, currently we are primarily dealing with 4G, and 5G is knocking the door, and we are actually researching on 5G plus these days, actually. So however, from the technology development perspective in the country, unfortunately, we have not contributed to technology development, particularly in communications area for 2G. We have been users actually from 2.5G, I would say. 2G per se, 2G we did not even start. We started in 93 somewhere. Mobile telephony started. That was actually 2.5G, and then further the LTE Advanced. LTE Advanced is actually the 4G, and then we are here now. So the key differences for 5G, the key aspects are I have highlighted here in a few bullets. So the rate of data, we are talking about somewhere from 1 Gbps to 10 Gbps user rate, remember, this is not the link rate actually. This is in contrast to the conventional, if you talk about 2G, we started with a few hundred kbps, in fact 200 kbps, and currently we are targeting, if you talk about 802.11a, 802.g and E is the QoS provisioned 802.11, where we talk about 54 Mbps, whereas we are talking about in 5G, we are talking about 1 to 10 Gbps. This is one of the main features. So ultra high speed. Then ultra low latency, we are talking about latency on the order of 1 millisecond. So to give an example how this latency is ultra low, if we talk about satellite communication, our satellite communication propagation delay, end-to-end propagation delay is on the order of 250 millisecond. So for the human voice intelligibility, the delay requirement is somewhere 150 millisecond or around that actually. So and in 4G we normally talk about 10 plus millisecond. So if the latency requirement, this is round trip delay, remember this is not one-way communication, round trip delay. If the round trip delay is less than 10 millisecond, normally we talk about the ultra low latency. So 5G targets ultra low latency. So again, the usage for ultra low latency and ultra high rate are to do with time critical applications, machine type communication, where a remote control is going to act on real time on actuating certain devices or certain action making process. So that is why this ultra low latency is of importance. And then ultra high reliability. So this is the third feature. Here, normally in wireless communication, we used to be comfortable with 10 raised to minus 3 bit error rate. We used to talk about 10 raised to up to 10 raised to minus 6, which was supposed to be very good. In fact, in LTE, we talk not less than 10 raised to minus 6. Whereas in ultra high reliable communication, we are talking about 10 raised to minus 9, 10 raised to minus, in fact, as low as 10 raised to minus 15 bit error rate. Okay, so which is very, very critical aspect also. Then wide communication coverage. So these first three features are the core features, I would say. So in the 5G core network, these are the three aspects that are supposed to be fulfilled: ultra high speed, ultra low latency, ultra reliability. Now 5G actually is in a sense very different from so-called evolutions from 3G, 2G, 3G, 4G. In between we had 2.5G. The difference is that in this evolution from 2G to 4G, we were only talking about increasing rate, and so on. Here in 5G, first of all, it is trying to encompass any kind of communication devices. For example, sensor network was not part of 4G per se. 3G, 2G, we did not talk about these ad hoc network, sensor network, Iot 211. These were not part of these evolution of these generations, so-called, in terms of communication. So the communication 2G, 3G, etc. These were primarily from telephony. Then we currently in LTE 4G, we are talking about video telephony. Whereas in 5G, we are talking about all pervasive communication, which means two things. One is that the communication, there could be low rate communication also, NB-IoT, for example. IoT is Internet of Things, narrowband Internet of Things. These are also part of 5G. And also these 5G also considered that one of the aspects of 5G should be all pervasive communication, which means that rural communication in Indian perspective, in developing countries perspective, this is one important feature actually. We have a significant deficiency of rural broadband coverage. So 5G is supposed to also ensure or provide this rural broadband connectivity. Now, how to achieve that? That's a different research aspect. We will not talk about in detail in this talk, but this is also one of the aspects that we have been working. Third, fifth bullet is massive IoT connectivity. So as I mentioned, because 5G is an umbrella actually. In fact, a good thing about 5G is that anything that we are working on telecommunication, communication related, connectivity related, we can claim ourselves in a sense that, okay, we are doing something of 5G. I'll actually give more glimpses as we move on actually. Now, massive machine type communication is one of the 5G aspects, because we are talking about, for example, smart farming, smart agriculture, smart city, remote surveillance, where we expect to deploy hundreds or thousands of miniature, specialized, low cost the nodes, which we call IoT. Why this is different from sensor nodes in terms of terminology? Because these are now supposed to be connected and should be controllable remotely. So now a large number of devices might be interested in communicating to a nearby gateway, and that number could be significantly large, on the order of thousands. In fact, somewhere, if it is more than 1,000, then we call a massive machine type communication, 10,000 or so number actually. So which means also that the communications of multi-access protocols that we normally are used to deal with are supposed to be relooked for massive machine type communication. And why machine type communication? Most of the conventional cases, again, 4G and below, we used to talk about human-centric communication. Here in 5G, human-centric communication is still going to be existing, but there could be significant emphasis on machine type communication. That means the machines, the IoT nodes will talk to each other and then make decisions for the system as a whole. For example, smart manufacturing is a machine type communication. Depending on the precision level of the finished product, it will possibly send instruction to the backward downstream in the production line to correct the production process so that the accuracy of the produced output can be controlled. This is one example of machine type communication. Smart vehicles, vehicular communication is also one machine type communication you can think of. Robotic surgery, any robotic automation are also machine type communication in a sense. Now here, normally robotics exists, but here these robots, we are talking about remotely controlled robots. So that is why the communication aspect comes into picture. The last bullet, and it is where I am going to focus actually in today's talk, is energy sustainability. So when 5G standard was conceived by these the forum, these researchers and technologists, one aspect that came into picture big time is that as we are going for more and more devices, we are talking about millions and billions of IoT devices to be connected, we have to also think of ways to make them energy sustainable. And as we know, as we go on one hand, we are talking about our mobile gadgets. In fact, some of you might be already experiencing that if you use all day basic phones like all day Samsung phones, they will last maybe for 5 days or 3 days without recharging. Today's phones, smartphones, unless we recharge almost every day, we cannot survive. That is because we are most cases we are talking about video connectivity possibly. We are a lot of video exchange is going on. So because of the high data rate, the energy drainage is also going to be faster, which means that in fact, that also makes us uncomfortable in terms of our usage perspective. We would like to make them more sustainable and maybe automatically recharging. And in some cases, we possibly would like to go for green communication so that as we go from technology advance, it does not also constrain on our energy requirement. Because energy footprint is a big question, carbon footprint, all of us know actually. Okay, so that is in a sense summary of overview of 5G. The other aspect of 5G is the softwareization actually. So when you talk about 5G systems development, we are talking about more softwareized systems in a sense that we have possibly some basic, let's say, software defined radio modules, and this can be programmed for different purposes. We can customize these modules for different purposes. So that is why these SDN, these software defined network, this network function virtualization, these are also part of 5G efforts actually, the softwareization actually, which is actually good for the country, for India, because India has strength in software. So which means that if we leverage our software skill, we can possibly contribute to 5G. And in a sense, we have significant emphasis. I started with saying that in India, we have not contributed to the standards of 2G, 3G, 4G. In some sense to do with our focus was something different. In 5G, we have an opportunity in the sense that IoT is also incorporated part of 5G, and also software and also makes us more comfortable to claim that we can contribute to these systems. Okay, so to summarize that, I'll move on to the next step actually. So this is broadly my overview of my research, so on one hand, I am working on the low power applications, primarily from energy sustainability perspectives. So that's why I placed this in a green bullet. and other is more of quality of experience, quality of service, quality of experience support for broadband services. So there are several subtopics: energy sustainability, RF, energy harvesting, energy transfer, data-driven learning, machine-type communication, edge intelligence, smart grid networks, and IoT are the aspects. In this discussion today, I'm going to focus primarily first two bullets: energy sustainability and energy harvesting, energy transfer aspects. And there are other aspects also on millimeter wave communication, rural broadband access, ultra low latency communication, ultra high bandwidth communication, and UAV aided communication 3D network. Actually, UAV aided communication can also be part of these, the either side. Actually, this is somewhat broad classification. Okay, so I am moving on. If there are questions, please make your notes and we'll come back to these slides if required. Okay, so now, so I have a collage of research problems that I have worked last over 10 years. These are some key publications, but there are a lot of additional publications along that line, which I did not present a cite over here actually. The topics that we are going to talk today is network or ambient energy harvesting. So again, the focus of my discussion today is going to be energy sustainability and energy harvesting. And more specifically, how we have perceived a research problem, and then how we moved from one problem to next and so on. This is kind of a genesis of research thoughts and execution. So that is what I'd like you to take away. And the slides are very compact. For maybe sometimes one slide or two slides are capturing one paper, which is a lot condensed actually. So, but again, I'm going to give the glimpse of the problem and the motivation of the problem, and then the crux of the idea, and then I'll move on to the next problems connected. So charging time. So some of the issues that we are going to talk about is the multi-hop and multipath RF energy transfer, charging time characterization, optimum relay placement. So again, these topics are kind of abstract right now, but we'll understand what we mean by this. Optimization for on joint information and RF energy transfer, relay powered RF energy harvesting, WSN, wireless sensor network, and dual powered communication, broadly from communication network perspective, not necessarily from IoT perspective. So now let us consider a scenario where we have, let's say, deployed miniature nodes, let's say for smart agriculture. Some nodes are deployed for monitoring certain activity, let's say humidity, temperature, and some other parameters could be. So, and maybe the pollution level, let's say. Pollution monitoring is another big time application actually. So let's say we have some nodes, and let's designate these nodes as the blue nodes actually. So these blue nodes, we are why this energy harvesting problem is very interesting or important is because we are going to deploy these nodes in large in number, which means that it will be very difficult to go and replace batteries, which is not convenient. And also, even if we go and replace the batteries, in those moments, those nodes will have to be dysfunctional. And in many cases, we cannot go to field because of the hazard involved to replace the battery. So we need to have mechanisms to recharge them actually. So this problem actually is a genesis of our interference temperature measurement actually. So we were trying to capture when, let's say, some red nodes are some nodes, let's say, some a hierarchical network. Red nodes are, let's say, in a higher tier, and the blue nodes are in the lower tier. Let's say red nodes are talking to each other, and then blue nodes are deciding when they should communicate. So normally these the communication in multi-access scenario happens by something called CSMA, the carrier sensing multiple access. And if we talk about wireless, this is normally the basic communication protocol is called CSMA-CA, collision, the collision avoidance part of the your carrier sensing multiple access with collision avoidance actually. So to avoid collision, so-called, what these blue nodes used to do is measure the signal power that is currently available around itself. So the node which is going to be transmitting something, it momentarily acts as a receiver. It tries to receive tries to capture the signal around it. And then if the signal level is above certain threshold, then it declares that the channel might be busy. So let me not talk right now. So that is the collision, the carrier sensing part actually. So, and collision avoidance I'm not going into. So now the question is that when I am interested in instead, let's say blue node is interested in energy harvesting. So earlier this blue node was trying to capture the signal level to ensure that it does not initiate a communication when the signal level around it is above certain threshold. Now blue node can play differently, saying that, okay, if let me check what is the energy level around me in my operation range, operation frequency band. And if the signal level is above certain threshold, let me not communicate, that is fine, because I don't want to interfere with others. But I can possibly activate my energy harvesting module to harvest the RF energy that is available for recharging my battery. Battery could be a supercapacitor. So that is the in-network energy harvesting. So now in fact, thermodynamically, it can be shown that this normally does not work if everyone is trying to harvest, because if everyone is trying to harvest and operate based on the harvested energy, then basically it violates the thermodynamic principle, which I am not going into detail. So we are considering that there is let's say another tier node which are possibly somehow powered. Let's say red nodes, they are maybe powered by solar power or maybe battery power grid connected. So red nodes are not now talking to each other, and these blue nodes are trying to harvest energy from the red nodes activity. And as and when blue nodes have certain energy available, they will try to communicate. Okay, so remember that the blue nodes are the miniature sensor nodes. Their job is to sense the environment and then time to time send the sensed information to the gateway node. Gateway node could be one of the red nodes actually. So very quickly to move. So this is the concept that I was talking about. So in this study, what we wanted to do was, can we capture how much energy is available if the blue nodes try to survive or try to operate based on the energy available from the network communication. So we call network harvested energy. This is like I am trying to harvest the RF energy available around me, and then I'm going to communicate whenever I am having sufficient energy. So what I quickly move. So several, because I have taken a lot of time to explain these motivation here. So what we see is that so if the energy harvesting efficiency is 1%, 1% is very low as a number, but if we are talking about very low energy available, RF energy available, for example, when these nodes talk to each other, on average, the RF energy available, RF power available is on the order of -43 dBm. Average RF energy is about -43 dBm. So now, why I have given these numbers 1%, 2%, up to 10% of efficiency, rectification efficiency, is because remember that rectification. So basically what we are talking about is that the RF energy is like electromagnetic waves. And let's say this can be, if we do Fourier signal analysis, this is basically a superimposition of multiple sinusoids. And then if we pass them through a rectifier and then charge the rectified signal, if we subject to a capacitor, then capacitor can be charged using the rectified DC signal. And that capacitor can be, the capacitor voltage can be used as the reservoir. Capacitor energy stored, it can be used as reservoir, which can be used for its own communication or other activities. So the typical energy harvesting sensitivity, so these are a lot of details I cannot go into, is that for the rectification purpose, the hardware that is available operates somewhere at about -20 dBm or higher, -10 dBm, -5 dBm or so. If the receive power is on that order, then it operates reasonably well. For example, if the receive power is let's say 0 dBm, the rectification efficiency could be as high as 70%, whereas if the energy available is -10 dBm, then the rectification efficiency could be maybe 20%. If it is -20 dBm, rectification efficiency is 10% or so. Whereas, as I mentioned, I am talking about if I am trying to capture the ambient RF energy, the energy available, or rather power available around the receiver is on the order of -43 dBm. In fact, there is no currently rectifier designed which operates at that low power. So, but still I gave some, I have taken some number. What we are saying is that if I have leakage is about 30 picowatt. These are from some papers actually. These are if you go into this was 2010 ICC paper. You will have all the details about rectification efficiency, etc. So if I have 1% rectification efficiency, then every 140 minute the node can send a pulse of data. If the rectification efficiency is 2%, every 69 minutes it can send a pulse of data. If rectification efficiency is on the order of 10%, then every 13 minutes, then the node can communicate. So on the other hand, if we change the leakage value, so leakage value just to play with actually, what is the, so why again leakage value I have considered as a factor here, because this 30 picowatt leakage of the microcontroller was in that time up-to-date design actually. So if we talk about CC2520 RFIC, its leakage is much higher than 30 picowatt, which is on the order of nanowatts actually. So what I showed here is that if I operate at zero leakage, then my for 1% rectification efficiency, in fact I have considered here, so your operation could be every 13 minutes. If I have considered 30% 30 picowatt leakage, then it is nearly 13 minutes only. If I have 1 nanowatt leakage, then 16 minutes. If I have 10,000 nanowatt, this is not feasible actually. But this 10,000 nanowatt corresponds to 10 microwatt actually. So these are the typical leakage that the microcontroller currently have actually. So what it means is that if we talk about current day practical microcontrollers, they cannot be operated based on the harvested energy from the ambient. So this was kind of a theoretical study that we wanted to do to see at what point our ambient harvesting energy could be useful, and we picked some number and we showed the usability. The card below has some other detail which I am skipping right now for the sake of time actually, because I have a lot of other things I wanted to discuss. Right. So this is so to summarize here, we wanted to see if ambient RF energy is sufficient to make some sensor nodes operate or to let some sensor nodes operate in the field. We see that this is rather hard to operate. If the node is very close to the transmitter, then you see these plots are showing that the duty cycle is going to be more and more if the normalized distance from the transmitter nearby red node to the blue node is more, my duty cycle is much higher, which means that rather duty cycle interval between one sample to the next sample is going to be higher, which is intuitive actually. If the blue node is close to the red node, then the communication, because it can harvest more, it can communicate at a faster rate. Okay, so this concept of RF energy transfer is what I am trying to propagate now. So on one hand, we see that if I am trying to rely on the ambient energy, ambient RF energy particularly, this is still not ready as a technology to use. So then we wanted to explore some other mechanism that can RF radiation be used. To remember that we normally do not talk about the charging by RF radiation. Okay, we talk about some wire connectivity. For example, if I am charging my phone, I'm connecting from the power plug through a cable to my phone, and it is charging through cable actually. So the wireless charging, if we talk about, there is a technology. In fact, the couple of technologies that came from MIT. So one of them was the electromagnetic coupling based. This is basically transformer principle. So based on the magnetic coupling, one can transfer energy from the primary coil to the secondary coil. Primary coil might be connected to the power plug, and the secondary coil is in place with the mobile phone or maybe the car. So electric vehicle, or not electric vehicle, rather we are talking about the electric vehicle, right? So electric vehicle charging, we are talking about, currently we are talking about wireless, we are talking about wireline actually, sorry. But there is a wireless version that is being explored that is actually magnetic coupling based, which means that in the electric vehicle at the bottom, there will be a huge coil, which is secondary coil. And then the vehicle will be going to sitting on a platform in a charging station. Charging station will have a primary coil, and then primary coil will induct energy to the secondary coil, and it will be operating that way. So now what we are trying to explore is not that actually. We are talking about RF energy transfer, not magnetic based energy transfer. So electromagnetic radiation based transfer, so which is very different actually. So this technology originally also came from MIT. Now what they have demonstrated was that it is possible to radiate energy to a harvester node with some rectifier diodes. This is called rectenna. And then these rectifier diodes will be collecting these wave fronts and then rectifying the signals. And there is a charge boosting mechanism. There is a principle called Dixon charge pump based. And based on that, they have actually a product, PowerCast. This company is called PowerCast. So the previous one, magnetic coupling based, that company is called Electricity. And the second one that I am talking about is PowerCast actually. So PowerCast actually came, I'll go to, this is the device I'm talking about actually. So this is the PowerCast technology. There is a module they developed, this is called energy harvesting board. And there is a, let's say, energy radiator. Energy radiator could be any microwave source, which is operating at a desired frequency, let's say 915 megahertz or 2.4 gigahertz. Now, what we were interested, so fine, they actually came up with a proof of concept and hardware demonstration that this is actually commercially available, and we bought for our experiment. So we thought, okay, this RF radiation based approach is fine. This is not practiced primarily because, in fact, I have some slides here. So basically, the motivation here is the energy capacity is limited, and there are ways to recharge actually. So ambient harvesting is actually dependent on the energy availability, which is not good, which is not practically feasible sometimes, because if I have to do some dedicated operation, I cannot rely on ambient source. So that is why dedicated charging is important, right? So I mentioned here that solar, vibration, wind, water current, etc. We are not talking about solar, vibration, wind, etc. Remember that these are all ambient. Okay, these are not dedicated available. So we want to have something reliable actually. So reliable on demand. And these for these are the two categories that I was talking about. One is magnetic coupling based, another is RF energy transfer, the electromagnetic wave front based, wave from radiation based actually. So we are talking about radiative energy transfer. So now for the radiative energy transfer, this is the basic technology that has been existing in the market already. What we are interested is doing something called energy routing, which is totally new. Actually, it has not been explored before. The idea is, so what we have shown that this process of energy radiation based charging a node is doable, but this is significant energy loss happens. As I mentioned, if my receive power level is minus 20 dBm, my rectification efficiency is on the order of 10% or below actually. Now, if I am transmitting from a node 1 meter away and the radiation power at the transmitter is maybe plus 10 dBm, my receive power will be on the order of minus 20 or so. If I'm 1 meter away, or maybe, so basically not more than 1 meter or not more than 10 meters actually. So I am radiated, which means that I am transmitting energy out of E energy. I am losing out 90% of that, and only 10% is being actually useful. So we wanted to see if we can do something better actually. So now, because this is radiation based, and what happens is that out of this radiation, these only a fraction of the wave fronts are being received at the receiver antenna. Majority of the electromagnetic wave fronts are going away. So I could think of placing a dummy node, let's say nearby, maybe on the right side or any other side, let's say. And then this dummy node could capture this radiated unused energy, and then that energy could be used for charging that dummy node, which does not have its own energy supply. So these dummy nodes in this diagram are the nodes here. Let me try to take it. Yeah. So hopefully this drive is available. So this is a dummy node, and this is another dummy node. This is we call multipath energy transfer. So idea is that this is my energy transmitter microwave source, hammock microwave source that we have used. It radiates. Its radiation power is plus 13 dBm, and there is a energy harvester node which I am interested in charging. So I have used, actually we have used here the PowerCast harvester with its own antenna, 6 dBi antenna. And what we wanted is that we wanted to capture the radiated energy that are otherwise going waste. So we placed a dummy node here, and likewise in this, for our demonstration purpose, we placed a dummy node on the left side also. These dummy nodes do not have their own energy supply. Remember, these dummy nodes are having their own also energy harvester, and then energy harvester is storing the energy, harvested energy in a supercapacitor, and as and when supercapacitor has certain energy available, it triggers its transmitter, and then this radiates energy to the this node. So which means that I am not obstructing the main line of sight, main communication is going on, and I am trying to make use of the unused energy, which is anyways wasted, to make them useful for increasing my energy harvesting efficiency, or to increase my energy charging rate actually, right? So this is what we wanted, is that we are going to later on call this as energy relay actually. These nodes can be considered as a energy harvesting energy relay node. Energy harvesting because they don't have their own energy supply, and they are relay node because whenever they have sufficient energy, they will be relaying the harvested energy, maybe a fraction of it, to these nodes. So why we are interested in? Because there could be many scenarios where we might have to, let's say there are field deployed nodes, and there is a mobile vehicle, maybe mobile robot goes around, and it goes around, collect the data from the field nodes, and also the mobile robot has a backpack of energy supply, and then it just radiates to that node and then charges that node and then moves on to the next node and does the operation. So that was the motivation, practical motivation where we want to apply actually. So this example I have drawn for a 2D example, terrestrial, but this can be also considered for a 3-dimensional, which we have explored later. Okay, there could be a UAV robot, flying robot, which could be going around and then collect the data, charge the node, and then move on actually. So now this is definitely much beneficial because if I go about magnetic coupling has its own challenge actually, because this requires a very perfect alignment, otherwise it does not work. Whereas if it is radiation based, that perfect alignment is not that critical and alignment can be done rather more easily. That is one advantage. Other advantage of RF energy transfer using RF is that I can also transfer information along with the energy. So moving on, so I'll skip through these experimental details. So this is the, again, let me go directly to these things. So this is how the charging of the intermediate node is happening. So these are the three different cases we have considered depending on the position of the intermediate node. What is happening is that intermediate node is charging. These are actually from the scope data. These are not handwritten actually. These are captured. In fact, as you can see here, this is from scope, oscilloscope. This is how the charging and discharging is happening actually. So the intermediate node is charging slowly, and then whenever it got a certain energy level, then it sends a packet of energy to the desired receiver, and then it exhausts in energy supply again, and it goes back to the charging mode. This is like a sawtooth wave actually. So for this, we have considered different placements of the intermediate node, and then we figured out that this placement of the intermediate node is actually very critical. So, but this is what is the charging process. If the placement is case A, case B, case 3 are 3 different places here. In fact, I mentioned here, case A corresponds to the intermediate node is close to the source. Case B is somewhere at the intermediate, and case C is close to the receiver node. So now this actually, so one thing we did is that we have tried to demonstrate that multi-hop energy transfer is actually beneficial. In fact, we have some data. Okay, so these results are placed, I think, right here. So as you can see here on the table on the right side, we see that if we want to increase the voltage level by using our multi-hop energy transfer, my efficiency of charging can be increased somewhere up to 10%. If we go up to 3 volt level, my rectification efficiency can be up to even nearly 29%. So which means that by using the so for doing this experiment, actually we did not have an energy router. Dedicated energy router is not available. So what we did, I don't know if you people are used to mica modes. There are sensor nodes. In old days, there was a company, Crossbow, they used to manufacture mica modes, mica 2, mica Z, Zigbee compatible, and so on. So mica 2 is the mode that we used for this experiment. And this mode was not actually designed for this energy routing, but we have kind of programmed intelligently to make them act as an energy router. So we removed the battery. So remove the battery, replaced by that energy harvester node with a supercapacitor, and then we triggered the transmitter as and when the supercapacitor has the voltage level above certain threshold. Right. So in fact, that was one point to note here, that we have tried to customize a node which was not designed for energy routing, and as a result, that also was one reason that we did not do much better. But yet, without with the off-the-shelf hardware, we are able to achieve up to 30%, 29% gain compared to direct charging. So meaning that if I try to do direct charging versus if I place dummy nodes which do not have their own energy supply, I can increase my rectification process or charging time significantly, nearly about 30%. Now, so that is one point which was actually motivating. A lot of challenging aspects was there. Now, other research problem that we picked up from here is that why the node position is so critical, why the mid position is performing my rectification process is something and so on. So if we consider these three cases, we see that the red one is the best to increase the voltage level at a faster rate. Red one is doing best. Red one is actually the case C. Case C is the right position, meaning that it is close to the receiver. So if the intermediate node, the energy harvesting relay node, is close to the receiver, in this scenario, we see that your charging process is the fastest. If on the other hand, if the intermediate node is at the middle, which is case B is the black plot here. So center position, if the intermediate node is at the middle of this distance, if we go back here, so this is the middle position. If I try to be close to the receiver node, which means that I am placing the node somewhere here. If I am trying to be in case A mode, I am going to be closer to the transmitter actually, right? So that actually also gave us a research problem, that can we characterize, or can we theoretically characterize why this is happening, and then come up with a theoretical claim that what is the optimal position for a transmitter to receiver energy transfer. So remember that in this case, we are not obstructing the main line of sight. We are trying to aid the direct energy transfer by doing relaying. Okay, this is from the communication perspective, this is a kind of a decode and forward and amplify and forward information transfer equivalent concept, but this is for energy transfer. Okay, so again, I think I am going rather quite slow given my number of slides that I have. So this is the one problem that we wanted to characterize, that what is the optimal position of the intermediate node. Okay, so for that, so this is one research problem, theoretical research problem that we generated from the experimental study that we started. We actually started our experiment in somewhere in 2007. Originally, we conceived the problem in somewhere in 2007. 2010 or so, we got a conceptual paper. 2012, we got some basic proof of concept. And this, we are talking about this paper that I am presenting here in this slide 17. This paper came in 2015 actually. Theoretically, we wanted to characterize what is the optimal position. Okay, so so this was a 2015 transactions on communication paper, which so there are two aspects of study. One is that because I do not want to obstruct the main line of sight, this is the RF source, microwave source, and this is the energy harvesting node destination, and this is my dummy node, which is supposed to be energy harvesting relay node actually. So I am interested in positioning the dummy node optimally so that my energy harvesting process for a given transmitter receiver distance could be maximized. So what I had to do is that I cannot obstruct the main line of sight. In fact, when we are doing experiment, we figured out that if the dummy node, this node, R node, is placed such that there is some little obstruction to the main line of sight, my performance of the rectification process is actually faster, but that cannot be used for theoretical characterization because I cannot use the electromagnetic theory equations if the main line of sight is obstructed, meaning that the wave fronts are distorted at the receiver antenna. Then I cannot use my conventional theory for doing this study. So we had to ensure that the main line of sight is not blocked. So this rectifier node or relay node is supposed to be placed in some place which is, we have called, this is a box constraint within this rectangular box. rectangular box is placed in such a way that it does not obstruct the main line of sight. Okay, so that was one aspect. I'm quickly skipping. This is the optimism formulation. Now there are two optimism formulations we had to do. One was that if so another important aspect to consider before we go to two optimization problems is that remember that this red wave front is coming continuously and the blue wave front is coming intermittently. Okay, because whenever the relay node has certain charge, it will transmit a pulse of energy, and red node is continuously sending these wave fronts, and blue node is sending sometimes some energy, right? So the question is that when the blue node is sending this energy and the red node is also sending energy during those moments, in fact, in our experiment, these moments were about every maybe 4 minutes, this blue wave front was coming for 4 to 6 seconds. Okay, so during these 4 to 6 seconds, this blue wave front and red wave front both are coming to the receiver node. Now, if these two wave fronts are coming in a destructive interference fashion, then actually they could actually kill each other instead of aiding the process of energy harvesting, right? Because if the two wave fronts are destructively interfering, that could be actually harming the process. On the other hand, if somehow I could ensure that the blue wave front and the red wave front are actually in phase, then I could actually do much better in terms of beam forming actually. So now going back to our original experiment, the hardware that we had available at hand does not allow us to ensure that the blue wave fronts are coming in phase always with the red wave front. So which means that in reality, the blue wave fronts are sometimes constructively interfering, sometimes destructively interfering. So we are getting some gain, but this is kind of an average gain. So that is why we, for the theoretical purpose, we considered that if we are able to do if we cannot do this beam forming, then what is my optimal position? That was one aspect of optimization. Then we theoretically assume that let us consider that the beam forming is possible. Under that condition, what is the optimal position of the red node, the relay node actually? So that's why two different optimizations came actually. But also remember, this is another interesting research problem that is of interest, because we are here theoretically assuming that your beam forming is possible. In that case, what is the optimum position? It can also be theoretically shown very easily that if the beam forming is achieved, let's say this red wave front is by itself giving power P to the receiver, and blue wave front is giving another power P at the receiver. If I do destructive, if somehow they interfere destructively, then the net power could be even 0, because as you know, actually this is if they are destructively interfering, they will kill each other actually. But on average, it can be shown, let's say I have V1 coming from one and V2 cos theta coming from another. And in this case, V1 plus V2 cos theta square is my normalized power. And if theta is random, uniformly distributed random variable, then it can be easily shown that this net power gain, if red is contributing power P and blue is contributing power P, then the average power gain without beam forming would be 2P. On the other hand, if I have V1 and V2 cos theta, and cos theta is somehow ensured to be 0, then my total power by constructive interference could be 4P. So individually they were contributing power P. If I don't do anything, if the power is averaging out, constructive and destructive interference is averaging out, then my net power will be 2P. Whereas if I somehow can ensure beam forming, my net power could be as high as 4P, which means that if I have n such transmitters with n different colored signals coming to the receiver, each contributing power P, then if I make them just incoherently collected, then the total power will be n times P. If I make them coherently collected, then it could be n squared times P, significant actually. So there is a significant benefit, and that is another direction of research that we have been pursuing actually. In fact, we have submitted papers very recently in that direction. So I'm going to skip that discussion, but motivation for assuming beamforming was coming from that, because if I somehow could achieve beamforming, that gives me significant benefit actually, square law power gain actually. So I'm skipping that these optimization formulations. And in fact, this was this plot at the top is showing that certain positions of the relay node is enabling beamforming positions. These yellow zones are beamforming zones actually. That if the red node, relay node is placed in that position somewhere, then the signal received at the receiver is always beamformed. Now, question could be why it is position dependent. Okay, so I'll skip the detail over here right now. Okay, so many other details here. So question is that if I somehow could do the beamforming, as you can see, my energy saving numbers are very significant. I'm skipping through. Okay, so that was one research problem that we generated out of our practical experimental exercise, that in the process of experimenting, we figured out that the position of the intermediate node matters, and we wanted to characterize theoretically. Another very interesting problem that also we generated here is that, remember that this charging of a supercapacitor can be considered as a most simple form as a RC circuit. Okay, there is a series resistor and there is a supercapacitor here, and then this is being charged by a source. Now remember, this source, in case of RF energy transfer based charging, this source is not a constant voltage source or not a constant current source, but a constant power source. So if we write the differential equation for charging this capacitor, where the source is a constant power source, P equal to V times I, which means that if I is reduced, V is increased, and so on. So the charging equation is no longer a linear homogeneous equation. So now question is why we were interested in that, because we wanted to first characterize how much time it takes to charge to a certain level. Because if I can do that, if I can estimate that if the voltage level of that node is V1, and if I have to go to level V2, how much time I need to spend for that node if I am that far distance away. Because that estimate will be telling me how many nodes I can attend and so on. Going back to my diagram, that conceptual diagram that I drew here actually. So there is a robot. This robot has to do some estimate, how many nodes it can charge, how many nodes it can attend, and how far time it will take to attend another node, etc. So we needed to know charging time actually. For charging time calculation, we figured out that the charging process is not a constant voltage charging process or constant current charging process, but constant power charging process. So we had to first characterize, solve that, and we have to capture the corresponding charging time. And again, I'm skipping all the details. This is a small, short 5-page paper you can look into. But using that, we have characterized the charging time required from voltage level V1 to voltage level V2. Okay, again, I'm skipping through details, but as you can see, the equations are not very simple because of the charging time equation. The differential equation is coming to be a non-linear, non-homogeneous differential equation, and process to solve it. So this is one quick module that I have just passed through. Another problem. So these problems are, remember, these are all internally generated research problems that while doing this experiment, we came up with these observations, and we had to characterize and study and delve into to solve these problems. Actually. So this is another problem that we have come across, is that this was our basic setup. Okay, this was the power cast harvester, power cast transmitter actually. So when you bought the power cast module, this is a development board, development system actually, the development kit. So that kit came with a 3-watt transmitter, although this transmitter is not very stable because a microwave source with a very stable transmit power is very costly. And we paid, I think we paid $300 only for this purpose. So this was my RF transmitter, power cast transmitter, and this was that receiver actually, harvester node with an antenna. So this was our tabletop experiment, or rather on the floor we were doing experiment. Now while doing this experiment, I actually unfortunately cannot ask you a question here right away. Maybe still I'll ask the question, you can come back later on, you can respond to me. That you might be aware of the free space formula. Okay, so antenna, if you have done antenna theory, you have studied this free space freeze formula, this is called. So which says that the power decays with distance as a square law in free space. Okay, so if my power transmit power is PT, at distance d, receive power will be approximately Pt over d raised to 2. Okay, so Pt times d raised to minus 2. Now in this, when we were doing this experiment, we were positioning these transmitter receiver node, we are varying the position, and we are seeing how far away I can move the receiver so that I can still harvest at a within certain time, etc. Very interestingly, we observed at one pattern that as we move the transmitter receiver node from the transmitter slowly, let's say at 30 centimeter, then 40 centimeter and 45 centimeter and so on, we see that instead of the power received decaying monotonically for different distance, it is actually oscillating. At certain position, although I have increased the distance, I was supposed to get a lesser receive power by free space formula, but I was getting more power actually. So the student was intrigued. In fact, I was called and we did the experiment, we repeated the experiment, we figured out that this is indeed happening. And we back calculated our equivalent path loss factor is coming to be not 2, but even less than 2. So we thought, okay, something is possibly, this is something definitely happening, but let us go to anechoic chamber and then do the experiment properly. So that was actually one motivation to do further digging actually. So what we now wanted is, again, this discussion is for the possibly for the graduate students who have done maybe studied Rappaport for communications, wireless communication. So in Rappaport, it has modeled a simple transmitter to receiver signal decay process as a 2-ray model. So one is direct line of sight, this is called LOS component, another is called non-line of sight component. So what was happening in this scenario is that there is a ground reflected wave front that is coming to the receiver, and that is sometimes at some position, these are constructively interfering with the line of sight component, and at those positions my signal level is going to be a little bit higher than expected. Remember, when we talk about free space formula, then these ground reflected wave front does not exist. Only you have direct line of sight component and nothing else. Okay, and in free space. Okay, so the your absorption coefficients, etc., are certain parameters, etc. So again, I'm very quickly moving through. I think so we wanted to characterize that. So this was again we. Several details we have to consider. So we so these are the different electric field components. One is for line of sight, one is for non-line of sight, and this is my effective vector length for the receive antenna. So many details I'm skipping. This was 2018 IEEE Internet of Things journal publication. You can look into more detail. So I'll quickly go into. So this was our experimental setup. For experimenting, and the theoretical characterization is what we showed in the previous slides actually. So we first ensured that this, what we saw in the lab experiment was indeed because of the ground reflection. So we went to anechoic chamber from a transmitter. This is my transmitter and this is my receiver. And receiver position, unfortunately, this anechoic chamber doesn't have the capability of changing the distance, but we could change the height. By changing the height, we could actually emulate this scenario also. So we wanted to do this study, and then we saw that by placing a reflector, the effect of reflector is actually causing different effects and so on. So we see that two things I will quickly consider as takeaways. One is that the optimal position of the transmitter with respect to the receiver matters. In this case, optimal height, because distance could not be changed in the anechoic chamber experiment. And another thing, curiously, was that the polarization of the signal matters a lot. So horizontal polarized signal, the reflection effect is very different compared to the vertical polarized signal. So again, many details are available in the paper, and I'm skipping through. So this is another research problem that the genesis was our original experiments that we conducted somewhere in 2007 to 12. Okay, so how much time do I have?
Sir, almost time is over. So you can conclude, sir, within 5 minutes, sir, so that we can have question answer session.
Okay. So yeah, so one thing that we discussed so far, two things we discussed. One was we tried to harvest energy, RF energy from the ambient, and we saw that the technology is still not ready. And but there are many other directions. Actually, I've skipped them. Then we explored what about RF energy transfer, and can we do multi-off RF energy transfer, energy relaying we call. And we got a lot of research problems, and some of them we have demonstrated here, how we picked up research problem, how we dealt, etc. Then the module that I wanted to show here very quickly is that now this RF energy transfer, there is an advantage, as I mentioned. So while I am radiating energy to this node, I might also radiate information to that node. So the same signal might carry my information as well as energy. So that is one benefit. And also maybe it could be possible that this is my field sensor node and this is my data collector. So data collector is actually interested in collecting data from the sensor node, and on the other hand, sensor node is interested in getting energy. So either it could be one-way process. So this is called simultaneous wireless information and power transfer equivalent scenario, where the source is transmitting information as well as power together in one direction. Or it could be wireless powered communication, where I am powering this node wirelessly, and then this node in turn sends me the signal that is available at that node actually. So it is two-way communication. So now in light of our experimental observations, we wanted to relook. Actually, there are a lot of theoretical paper, and we observed that these papers had did not actually consider this rectification efficiency factor so critically. And why this study is very, very interesting is because, remember, when I am talking about in information communication, information reception sensitivity is as low as -90. Even in the modern day communication, it could be as low as -102 dBm. So which means that if my received signal power is -100, -90 or -100 dBm, information can be extracted out of it. Whereas, as I have already told, my energy, if I want to use that RF energy for rectification purpose, the power level should be as high as -20 dBm or higher, -10 dBm or so, which means that for the same communication range, for example, if I am transmitting from the RF tower and at 100 meter away, there is a mobile node which is trying to collect energy as well as information, this is not practically possible. So SWIFT, simultaneous wireless power information and power transfer, practically is not possible because of the imbalance of rectification efficiency and sensitivity for energy transfer and information transfer. So minus 90 dBm versus minus 20 dBm. Okay. So same principle can be also considered to be applicable to argue how the wireless powered communication would work. So I'll quickly go into this diagram. So WPCN basic papers talked about that actually. So this is my the base station. Base station is collecting information from this node through this blue line, and then it is sending energy through this green line. But as I mentioned, for a given communication range on the order of 100 meter, this is not possible. 100 meter for any practical radiation power, charging a node at that distance is not possible. So we came up with something called relay powered communication network and swift variation relay powered wireless information and power communication and so on. So there are several papers in that direction. Again, I'm skipping through actually. These are many details, skipping through. So last module that I wanted to show is so now come back to the scenario where, let's say I am trying to harvest energy from the ambient, not RF but solar, because we know that solar is very prevalent, and in fact there are a lot of solar powered solar powered calculators we all of have seen. And likewise, solar powered sensor nodes are also possible. People are also talking about solar powered base station, but the challenge is that, so again, because the solar power availability is not guaranteed, and also there is an asymmetry between the traffic and energy. This is called traffic energy imbalance. So there is a requirement that if I am trying to charge my solar base station, which requires to be continuously round the clock to be operative, I have to also ensure that there is a parallel connectivity through the power grid, which means that as and when I do not have sufficient power through the solar power, I will be able to draw power from the power grid. And also it is interestingly, it is also possible that if I have surplus solar power, I can also supply that power to the solar grid, right? So this is the two-way power supply. But so this is people are talking about, but as communication engineer, what we are interested in is, if I have a networked base stations, normally the communication base stations are networked actually, right? Because one base station's data is a kind of other base station's performance, and they are controlled by something called radio network controller, and radio network controller is controlling n number of base stations. So there is a network connectivity actually. So we are talking about, can we do a networked dual powered communication where these traffic and energy imbalance can be judiciously managed. One example that I have taken in this presentation is about something called coverage adjustment. That means that if a solar powered base station is currently having deficiency of power but more traffic to handle, on the other hand, a nearby node might have surplus power but not so much traffic to handle, can they readjust their coverage ranges by doing because radio network controller can run that coverage, rerunning the algorithm, and then they could readjust. So instead of selling that surplus power from one node and nearby power might be buying power, if we do that, this is much more cost effective, and how much of traffic energy imbalance can be dealt with is one of the studies that we have done. So, and several variations. This is actually very, very hot currently. One paper that we have published, one is in the pipeline, and we are currently working on further actually. So some results here, that without coverage adjustment versus with coverage adjustment, see net profit, if we see that the net profit is increasing more and more if the skewness level of the traffic and energy imbalance is more and more. Okay, so that is a takeaway, that by allowing the nodes to talk to each other in a network fashion, my dual powered communication network can be much more beneficial. So this goes towards sustainable communication perspective. So I'm trying to be self-sustainable, and I am also trying to be green, and I am trying to see by making use of the network feature, which is anyways prevalent in cellular communication, can we benefit? So some of the results are presented here. So now I think because of lack of time, I will not go into any detail. So there are several aspects of other work that we have been doing. Distributed beamforming aided energy router design. This is one. Currently, we have submitted a couple of patents, and we are working further. Smart IoT systems. So one way to do the sustainability is how to let's say harvest, etc. Other way of sustainability is how to be intelligent, more and more intelligent in terms of what data to be generated, and if I have certain data generated, what data to be communicated, and so on. So we are working significantly in terms of applying machine learning for smart IoT systems. Smart grid communication. In fact, that is one of the IoT application. Actually, there are millions of smart meters going to be deployed for this purpose, and we are looking at the data where the smartness can be incorporated, and also machine type communication can be incorporated. Coexistent communication technologies. This goes towards broadband wireless access, remote, what is it called, rural broadband coverage. So this is another aspect. And also we have been working on at IIT Delhi, we have been working on industry academia collaborative communication setup development. So there is a consortium we have recently created. Idea is that we have a industry grade infrastructure available, which will allow us to translate some of our own research, and also will help us to compete in terms of product-oriented research output and so on. So very briefly, I don't have any other slides actually. So to summarize, so I think I'll skip through this, mentioned all these things here. So to summarize, we have talked about the energy harvesting and energy sustainability aspects, and I would be glad to take questions and explain whatever detail I can. Okay, thank you.
Thank you very much, sir, for providing us an overview of 5G and some of the research problems faced during research work on 5G. Now I request the participants to ask their queries. They can raise their hand one by one, or they can ask their query on the chat box. Sir, there is a query from Mr. Vishal in the chat box. Power increases in node. This happens due to constructive interference as the distance increases between the transmitter and receiver. This is the question mark.
Right. So yeah. So basically, this is to do with so-called passive reflection. So the ground reflected wave that is coming from the source, this is called non-line of sight signal. That non-line of sight signal is, if it is destructively interfering, although I am increasing the distance, I was supposed to have certain power level based on, let's say, free space formula. I know what is the power level to be expected, but I am getting less than that power level. Or if at that distance, at that position, the interference is happening constructively, then my receive power level is going to be increased. Actually. So basically, this is to do with the passive reflection from the ground surface. And because of the constructive and destructive interference, instead of the power decaying monotonically with distance, the decay is happening in an oscillatory fashion. Okay, hopefully that answers the question.
So there is another query that what will be the cost of these energy harvester nodes and lifespan of these?
So this is actually more at the research level, I would say. For the research proof of concept, one can consider to buy these modules. So as I mentioned, we have bought the PowerCast harvester and that was long back actually. This was 2011, 2008 and 2011. We purchased 2 modules and we paid, I think, about $300. Okay, so but this harvester, we have also our own in-house designed harvester module. So if we want to design these modules, this can be harvester module cost can be significantly reduced. But for the lab experiment purpose, you can start with these let's say available modules from PowerCast or equivalent company, and then start doing your experiment.
Okay, thank you, sir. There is someone personal question from my side. That there is one misconception in the social media that it relates 5G with its second wave of the COVID. So kindly throw some light on this.
I honestly speaking, I do not have any scientific view or scientific answer. In fact, I was not even aware that 5G is considered as one of the reasons for this thing. So I do not have any ready answer that 5G, how 5G is contributing to this second wave actually. So I don't speculate actually.
In fact, they have some kind of misconception about the radiation's EMF effect on some body or human body. This is what I understand.
No, so this is very valid. Actually, this is a very valid concept. In fact, of course, this is not properly proven, and this proper proof is not very easily possible actually. But radiation, effect of radiation on human health is in a sense proven. For example, high radiation. In fact, near the telephone towers, for example, telephone towers or let's say microwave towers for the mobile towers, the birds presence around the towers are reduced. In fact, birds normally do not go nearby the tower actually. That one shows that there are possibly some harmful effect. That is one way to capture it. The other way to look at, in fact, that is possibly much different aspect, basically effect of EMI, EMC on the human health radiation. But what I would take is that is one of the motivation for 5G to make things more energy efficient, so that to achieve the same objective of wireless communication, we radiate less. Okay, so the effect of radiation on human health or environment is a different kind of research. So EMI, EMC effect that is happening, but 5G communication community has taken in a different perspective, saying that, well, let us try to radiate as much as possible, as less as possible, for achieving our targeted wireless connectivity. For 2 perspectives, one is human health possibly or environmental hazard, but other is indirect hazard, is because if I am radiating more, I am possibly consuming more coal energy, fossil fuel, right? So to reduce the fossil fuel dependence, we could be more energy green communication capable, so that we do not rely on these sources, right? So that is how I would connect the 5G is contributing to reduce the effect of environmental hazard by being more energy efficient, more energy sustainable, and being more green.
There is another question. Will 5G implementation affect cybersecurity?
This is a yes, yeah, very right. But yeah, so cybersecurity in general is a key issue of communication system. Very key, very hot key issue. There is no specific requirement identified for 5G as such, but if we look at the 5G requirements, possibly the security features have to be relooked from that perspective. But it is true that the security features are a very valid aspect of 5G standard, and we might have to relook at the security features given the 5G requirements. So for example, if I am trying to be ultra reliable, one way of achieving ultra reliability is that I transmit more redundant information. By transmitting more redundant information, I might be making myself more vulnerable. Right, so I might have to look at the design policy to ensure that my vulnerability is not increased while I achieve these three ultra goals: ultra high speed, ultra low latency, and ultra reliable and massive connectivity.
Okay, thank you, sir. So I think there are no more questions. So may I request Dr. Rajesh Grover to kindly propose a vote of thanks and conclude today's session.
Thank you, Ritesh. And well, it's my proud privilege to have been asked to propose a vote of thanks at the occasion. And it was really an honor to have with us Professor Day from the Department of Electrical Engineering, IIT Delhi, to deliver a talk on the glimpses of 5G research at IIT Delhi. And sir, you talked about key features of 5G and gave an overview of energy sustainability, energy harvesting, and green communication. You also highlighted the research initiatives undertaken at IIT Delhi, especially on wireless RF energy transfers. And our heartfelt thanks to Professor Dave for sparing your valuable time and being with us to deliver an enlightening talk at the occasion. And I also take this opportunity to express my sincere thanks to Dr. Nirima Jareth, our worthy Director General, who she had to leave in between because of some other scheduled meeting, and for sharing her views and inspiring mentorship to organize these programs so as to provide a regular learning experience for our participants. And I also take this opportunity to extend my special thanks to my colleagues at Science City for having been associated directly or indirectly to organize this webinar and make it a success. And I am also thankful to our friends from print and electronic media for evincing interest in this webinar, as well as to our participants for being on board to join for this webinar. Thank you all. Thank you very much.
Thank you, sir. Thank you very much for joining us today's session.
Yeah, thank you. I hope this was useful. This was very, I had to rush through the topics, but I wanted to give a glimpse of our own research, and more importantly, how, as I mentioned, how our research thoughts actually moved organically from problems to problems, and we have been significantly actually branching out further in that direction. So I would like to consider that one as a primary takeaway for the research motivated audience.
Thank you, sir. Thank you.
Questions further, I would be happy to respond over email. I think that has been mentioned in my slide also, and you can search on the website also.
The entire session is also available on our YouTube channel also, sir. It was telecast live on the YouTube also. Okay, great. So yeah, so I'll be happy to answer more questions if that is there. Okay, thank you. Thank you. Sir. Thank you very much, sir.
Thank you. Thank you.
Okay.